Hi everyone, I'm Justin Whitfort. I am a co-founder and programmer at Samurai Punk. We've previously done a few titles, Screen Cheat, The American Dream. Today I'm going to be talking about a few of our newer titles, and that is Table of Tales, which we've done with Tin Man Games, and another small title we've been working on called Feather. So, alright, yes, that was the order. And I'd also like to give a bit of a shout out here to Edward Blanche from Tin Man Games. He's the technical artist on Table of Tales, and he's helped me create the rendering system I'm going to be talking about in this talk, and he's also helped me out with some of the slides based on a tech art approach to the same talk he gave over in the UK earlier this year. I did ask my own company's artists for some help, and all I got was this lousy image. So the first game we're going to be talking about is called Table of Tales, and if we are lucky, we should be able to get a trailer.
Your aunt left you something special in her will. A table, but inside this table, a whole world of cities and ships, swashbuckling and adventure, sword fighting and alchemy, and above all, a world of shadowy cults, dark gods, and scoundrels.
This is my Table of Tales. Let's play. PlayStation.
Okay. So yeah, there we go. So Table of Tales is a game where you're sitting in VR in front of this animating table. It's coming to life. It's bringing you different sort of settings and worlds. But that comes with quite a few technical challenges. So the biggest of those is that we have a really large number of objects that we've built all of these worlds out of. So you can see some townscape environments in there. All of those towns are built out of these, essentially lots of one-by-one blocks to make the core of the buildings, and all the tiles on the ground. And all the windows and doors and little bits of decoration are all separate objects. So we end up having a very large amount of objects in most of our scenes. The artist wanted all of these objects to be dynamically lit. In the end, we've got two spotlights. One of those spotlights is used for the artists, and the other is for the narrative designers to draw attention to things. And we've got 4 point lights as well. We've got shadows on the main artist spotlight. And we need all of these tables and environments to be able to animate and transition. So this isn't like 5,000 static objects, this is 5,000 moving objects. On top of that, we're running on PlayStation 4 at 60 FPS with 40% larger than 1080p, split across 2 cameras for each of the eyes. And that's a lot of pixels to be drawing every frame. And we also, the one advantage we do have here is that we have a static-ish player viewpoint, and that means you're going to be sitting in the one spot, looking at the table, and that means we're always seeing pretty much the whole world at once. And so we felt that going into this was fairly difficult from our typical games, and we're going to look at how we sort of looked at what we can do to take advantage of our situation that Unity might not be able to assume for the average game. So this is an example table transition. You can see all of these things popping in and out either side of the table. And so all of these objects need to be able to move at once. We also raise and lower tiles during gameplay to show where you can move, for instance, and target abilities and all those sort of things. So yeah, we need to be able to move everything. I'm going to briefly just do a bit of a background in the way Unity approaches its rendering. And that's an image of what happens when you write your own rendering system and you mix up matrices. So you probably, if you try it yourself, you're going to see a lot of things like that. So yeah, the first thing is how do objects get drawn in Unity? So there's a few stages of this. Hopefully a lot of you are already familiar with this, so I'll try and move a bit quickly. We start on the CPU. which is the main thread plus potentially some job threads and such. Every renderer in our game, something that gets drawn to screen, is going to have a mesh and material, generally on, say, the renderer component in Unity, and there's going to be an associated position and everything on the transform component. And when we want to actually draw the scene, Unity is going to gather all of that stuff together, and it's then going to have to figure out, okay, what is actually drawing this frame? So we're going to do some culling. We're doing, say, frustum culling, where we cull anything that won't make it onto the screen. If we've got it enabled, we might be doing some occlusion culling, that kind of thing. And after the culling, we're going to put all of these results into batches. So that'll be dynamic batching is one of the sort of faster ways to do it in Unity at the moment. You figure out which, sorry, not one of the faster ways. So dynamic batching is getting everything that's using the same material and at runtime putting it into sort of a combined mesh. We've got static batching, which is doing the same thing but offline. And then we've got instancing, which is typically the fast way to go to at the moment, where you go, all of these things are drawing the same stuff, so I'm going to tell the GPU to draw an array of them in these positions. Then we're going to have some kind of device thread, which is going to go, cool, now that we've calculated everything, I'm going to be talking to the GPU and waiting for it to finish, and it's going to send all those batches across. And then on the GPU, sort of at a very simplified level, it's going to have to process all the vertices, so it's going to run once on every vertice for all your vertex shaders, and it's going to run once on every fragment, which is potentially going to make it to screen as well. And we'll go into that in a little bit more detail. So this is what Table of Tails looked like in Unity's timeline view, with sort of our custom instancing methods turned off and some default-ish Unity rendering. So hopefully you can sort of see what's going on there a bit. Up the top, you can see the top row is the main thread. So that's where we're doing all of our initial culling and batching and stuff within the draw call. So all of the green stuff is the camera rendering and similar as a general rule. So you can see we're taking up a decent chunk of time. We've also got all of the worker threads below, which is sort of our render threads are spread across there. So that they are very easy to miss if you're just having a first go at profiling in Unity. Unless you go to this timeline view, all of that work will be completely hidden from you, and it might show up as waiting. You might think it's just waiting for the GPU or something, whereas you can still be very heavily CPU bound there. And then down the very bottom is the device thread, and that's the bit which is actually telling the GPU what to do. Typically, depending on how your performance is, that'll be broken up into two parts. The first part will be waiting for the end of the pipe, so telling the GPU what to do. And then the second part is waiting for present. So this thread isn't doing anything anymore, it's just waiting for the GPU to say it's done. So if you're actually GPU bound, typically you'll have the waiting for the end of present at the end there. Okay. So there were a few things that I'm not going to be going into in this talk, but that we have done in that previous graph already. So we've swapped from deferred lighting to forward lighting, but just going to a standard forward with the amount of lights we had would have been really bad because we're doing an additional pass for every extra light. So we've written a custom forward shader, and this is where Ed's work came into it a lot. We've written a custom forward shader which handles a fixed number of lights, because we always know we want to just handle the same number of lights. We just want to handle our worst case in this game, because if we can handle our worst case, everything else is just easier. And our fragment shader was still quite expensive, so we played around with drawing all the objects in the scene twice. The first time we just draw a depth-only pass, so that'll fill the Z buffer, and that way when we do the fragment shader, we're only ever paying for every final pixel on screen once. So again, we're just getting a more consistent cost. So yeah, with Table of Tails, we can know what is the worst case scenario, and that's when you're sitting back, you can see the whole screen. So we can start thinking, hang on, we don't need to be spending all this time Unity's doing on culling and doing all that frustum culling. And it's difficult, we thought at the time within this game, to have any other kind of, like occlusion culling wouldn't work for us because we can't bake occlusion culling because the whole table's moving all the time. So we just sort of figured, look, let's see what we can do. Can we turn off culling in Unity? And the answer is no, out of the box. But yeah, our big issue is CPU time. So it's sorting, it's culling, it's batching, all of these things over this many objects really starts to add up. But yeah, we have some other advantages. We do know how often these objects change. It's generally all of the batches. So a batch is just one type of object we're drawing a lot. These batches are a fairly constant size once they're created. We load in a map. That map exists until we unload the whole thing. And we do know when they move. And when they move, they often move in a pretty predictable way. Often we can get away with saying, look, we're only moving position. We don't even need to compute the change to the whole matrix. So we can start thinking about how can we take advantage of this. And the solution we've used is a method called graphics draw mesh instanced indirect. So at this point, we're no longer using Unity's renderer component. We're barely using transforms or any of that kind of stuff. We're just skipping Unity's typical render pipe. And we can say, hey, Unity, draw this mesh with this material and whatever information is on it this many times. And so at this point, the material is actually having some compute buffers set onto it, which are like GPU arrays. I'll go into them in a little bit. And we have two of those arrays on the material. One of them is an array of transform matrices, which describe where does this need to go in the scene. And the other one is a color array so that we can tint individual objects. Every frame, we only need to update the bits of the buffers that have changed. So if we've moved 10 objects, we can just only write into that little bit of the array. And we've skipped culling because Unity will now only try to cull each batch once based on the bounds which you pass in with this call. And so we just set a giant bounds of the entire table so that it'll never cull that. And that culling has become trivial cost. And down the bottom, you can just see a little bit of an example of setting some buffers, some draw mesh instance indirect calls. I recommend just checking out the documentation on this one, and maybe I'll see if I can post some better code samples later, but there will be a few more snippets throughout. So a compute buffer, it's an array on the GPU, but it can easily be updated from the CPU. Some of them can also be updated, depending on how you bind it, you can also update it from the GPU if you want to have work on the GPU feeding into more work, and we'll look at that later. So yeah, in table of tails, we have that color array and we have a transformer array. The interesting thing about that is while you think of when you transform a point, you use a 4x4 matrix, you've always got that last row is going to be 0, 0, 0, 1, so we can just drop that and send through 3x4 matrices, and immediately we've immediately saved 25% of that sort of bandwidth, which is a nice little saving. So when we send through this call, we're also passing through another compute buffer called the argument buffer. So, and that's going to have some information which is telling the draw call kind of how to work. We're going to have an index count per instance, and that is from the mesh, that's how much stuff's in it, and an instance count. Those are the main two we care about, and mostly we care about the instance count. That's the number of objects we're drawing. There is also, at the bottom, you'll note start instance location. It's a really handy thing in theory, and it only works on Mac, so I don't recommend relying on it. And Unity sort of have been happy to say, oh, it's functioning as intended. You have to sort of get at it yourself, even though we don't make it easy through any of our shaders. And who really wants to write a different shader per platform? So just find another workaround. So when we applied this method, you can see these are some of our initial results. And the way I recorded this, I recorded it with it on and then with it off. So just imagine this graph is flipped around if you want it to read nicely left to right. On the left is with the custom instancing on, and this is a frame rate graph. I'm not sure how easily you can see that from there, but you can see our frame time is roughly halved when we started applying this method. There are some additional improvements we got by changing the order we constructed the tiles to immediately feed into these buffers from front to back rather than sort of at random. Or I think we started in the back left and came to the right and then forwards. So we were kind of drawing back to front, which was the worst case. We're able to skip a bit of some rights, which can otherwise be discarded on the Z buffer. And yeah, a lot of just shader improvements, which I don't really have the time to go into today, unfortunately. But learning to use the GPU tools on whatever platform you're in can be really, really nice, especially if you're on the consoles. But even if you're on a PC, look into tools like RenderDoc, which has Unity integration, and you can do a lot more than you can with just the Unity's built-in frame debugger. So here's another view of that timeline from earlier, and you can see that the top one is without our custom instancing, and the left is with it. And we've dramatically cut down the amount of work in those render threads. I'm not sure if you can see the time improvements, but the graphs are at about the same scale, so you can see we've, pretty dramatically cut down on the time. About halved, as we saw in the other view. There were still some remaining issues that we had on the project. We couldn't get the depth texture without Unity having to re-render the entire scene into a render texture it was happy to access, whilst you get a depth texture that you can see in all your debugging tools and everything when you're working on these platforms, but Unity hasn't cheaply exposed it on most platforms. So it'll just, to keep cross-platform, I assume, they will always re-render the depth pass if you ever try to use it for, say, some screen effects or anything like that. We also had a weird issue on PlayStation where for some headset positions, as you move the headset around, you'd notice some objects in the world disappearing. We eventually realized that there's certain points where either one or two objects in each batch would just render with a 0 scale, the first two objects. And so our workaround for that was to just add 2 0-scale objects into the start of every batch, and no worries. So next I want to talk about Feather. So this is another game Samurai Punk have been working on. And it's just a really relaxing game. I didn't actually remember to download the trailer for this one. That probably would have made sense. But you can see a bit of a panning GIF here. It's just a relaxing game. You fly around, you explore the soundtrack and the island. And again, it's a scene where we're drawing a lot of objects. But in a lot of ways, it's kind of the opposite of Table of Tales, because suddenly we've got an entirely static world. The player moves a lot, and you're never going to see the whole world because you're in it. While you can fly up really high and look down, in theory, you're still going to have all these cave networks and things you can't see, and there's probably going to be some stuff hidden behind clouds or mountains or whatever. But it does have, we've got some similar traits to Table of Tales. We're still having big CPU issues with the amount of stuff we're trying to draw. And we've got the advantage. We know when stuff's going to move. In this case, it's never. But drawing that much stuff, it's still expensive. So here's an example of if you were to have a look using the hierarchy view to try and nail down the details. So you can see here, 43% of the time is in GFX wait for %. So this is on a console platform here. One of the we haven't actually announced what console platforms the game's coming to. So imagine it's sort of a small handheldy type console with a not that great CPU. But the GPU is still pretty good. So you can see here, all of our times in GFX wait for %. So I guess we're CPU bound. Not quite. If we swap in the top left, you go where it says hierarchy, you click it, you select timeline, suddenly you're on this view, and you can see on Switch, it doesn't actually multi-thread very well in that particular version of Unity. And the render thread is actually what's taking up most of the frame. So all of that wait for % is actually just waiting on the render thread to do its thing. And in this case, the render thread isn't even waiting on the GPU at all, really. It's just doing all of its culling and batching and all that kind of stuff. So, like in Table of Tales, our problem is getting calls to the GPU. I've got a touchpad here, which is just really easy to hit by accident. Okay, so, we just gone backwards. No, okay. So yeah, we can reuse from Table of Tales. We've got all these advantages. We just figured, let's try putting the same instance renderer in. Because, from that previous graph, we could potentially lose that depth pass, which Unity is doing, to get our screen effects, and we could maybe get to it. So actually, just to clarify, this was, I'm not sure if you can read it up the top, this is 68 millisecond frames, which means it's running at about 15 FPS. So we might be able to get to 30 FPS, which is our goal if we were to drop depth pass and all these other nice things and tell the artists they just can't have all the pretty effects they want anymore. But that generally doesn't make me popular at work. And there are parts of the world where our performance gets even worse. So we can get rid of all of that culling by using our draw mesh instance indirect again. There might be a little bit of extra overhead because we're drawing everything on the GPU and maybe our vertex shade is expensive, but we figured we'd have a look at it. And so this is with draw mesh instance indirect. And you can see it looks a lot simpler. Suddenly we're doing a lot of waiting on the GPU and our frame time has gone up to 90 milliseconds. So we've lost about 21. But you can see we're waiting on the render thread for 53 milliseconds. We're waiting on the GPU for 70 milliseconds. And this is good. This means that now we can have a look at how do we bring the cost back down on the GPU, because we know that the GPU on this platform's all right and the CPU is just never going to cut it. So what we can actually look at here is GPU culling. And so in contrast, CPU culling is what Unity was doing. All of the culling was being applied before we were making batches. We're doing all this work. The occlusion culling, which we did have baked into the level, was helpful, but we were still having big cost impacts on the main thread and the render thread, unfortunately. And so we're like, yeah, let's get rid of that. GPU culling, in contrast, is something we can do using compute shaders. So compute shaders, I think I've got a slide on them in a bit. It's a bit of code that you can run on the GPU that is kind of not tied to drawing polygons to screen. So in the GPU, we were doing a frustum cull on all objects, so we're immediately discarding anything that's not in the frame. We're doing a hierarchical Z-buffer occlusion culling pass, and so what that means is we're actually getting the depth map, either from this frame, from last frame. In this case, we're using that depth map Unity's already making for us, and we're sort of creating a mip-mapped version of that, and every step down, the mip-map is what's the furthest away position in this quadrant of the screen as it gets lower and lower res, and we can sort of test objects against that to see if they're going to be completely hidden by geometry. And the GPU is really good at doing this. And as an aside, I ran into this bug at one point, and it's what happens if you custom batch a static batched object at runtime by just getting all instances of a renderer in the scene and going, give me the mesh you're drawing, I'm going to draw at your position. And so we were drawing each static batch where Unity has combined all of these objects at the position of every one of those objects in that batch. It actually makes a really cool effect, and I kind of want to know what this game is, and if anyone wants to make whatever that is, I'd play it. This is a bit of a look at it in motion. I'm not sure what happened to the terrain, but I mean, it's probably for the best it hasn't drawn like a few hundred instances of the terrain, otherwise we wouldn't really be seeing much of anything. So yeah, this is an example of what the culling and feather looks like once you're flying around. So you can see as the camera frustum swings around, we're getting rid of everything outside of it, and everything that's kind of behind mountains and such is a bit flickery. That high Z pass can get a bit confused when there's edge cases, so things will flick on and off, but the main camera won't actually be seeing any of that flickering. For some smart reason, I've flown around near the origin, which at this stage of development is the buggiest location, so you can see the water rapidly changing colors. We're working on that one. That'll get solved. Yeah. So, yeah, GPU culling with compute shaders. Sorry, I have not got as much sleep as I was planning last night. I'm not sure who else was at the networking night. So yeah. All of our draw calls are now being sent to the GPU, but they're being based on information which is on the GPU, and that's that array of transform positions, and it's that args buffer which has the number of objects we want to draw, and we can write those from the GPU as well. So now we create an extra buffer, which is the input of all of those objects, so in an extra array of 3x4 matrices saying this is everything in the scene. And then we can run a compute shader, which will get this is everything, and it'll turn it into this is what's on screen. And it will alter the number in that args buffer so that we only draw those. So yeah, as I was mentioning before, compute shader, it runs code on the GPU without being part of the typical pipeline. So it doesn't need to have any vertices going into it or have associated geometry or any of that. So in a compute shader, we always run a bunch of groups, wavefronts, waves, or warps, depends if you're on NVIDIA or AMD hardware or whatever else, or however you want to think about it. These are always groups of threads. So like 16 or 32 typically threads running side by side. And they always run the same code at the same time. This is the same as in a regular shader, but it's less obvious there. So if we run through a shader, we're hitting the first line and we're running it for everything in the group. And that's why branching in a GPU is bad, because we're always going to run both branches. So you can probably imagine how if you have an expensive pass, and then you're like, okay, but if we're far away, I'm just going to if, and I'll do this cheap thing instead. And it sounds great, and on a CPU it'd work lovely, but on a GPU it's just going to do both. So like 90% of your geometry might be using this cheap version, even though you've just calculated the expensive one. Anyway, that was an aside. So all threads run at the same time, but in the compute shader, we can actually have some group shared variables which allow the group to share a little bit of data, and that'll come in handy later. So on the right, you can see an example of a fairly simple compute shader. We've got two buffers that we pass in up the top. We've got a structured buffer, which is our input, and a read-write structured buffer for our output. We specify how many threads this group wants to know about, so we can have a different number there, and it'll give us more things, more input numbers and such, but it won't necessarily. That's more about how the CPU dispatches these groups. So just probably ignore that line. And you can see in the main body of the method, we've got a dispatch thread ID. So when this gets called from the CPU, we'll say run it, say from, I want threads from 0 to 1,000. We'll pass in some things, and that dispatch thread ID in its X, say, we'll have from 0 to 1,000, and we can do stuff with that. We also have a local index, which is the index within this wavefront. So we can use that to do some smart things with our group sharing variables and cutting down on the amount of work we do. And in this example here, I'm just checking, should we frustum cull this thing? Should we high Z cull it? And if not, and it should go to screen, then put it in the output buffer. And then we'll do it. That's a very, very cut down. You'd need to calculate the index as well. So we'll go into a bit more details. So one trouble we had was when we tried to write this, AppendBuffers didn't run on our target platform. I believe they run now. I've just seen a report from Unity, but at the time they didn't, and this has actually allowed us to do some neater stuff anyway. So yeah, one of the big concerns, if we're not using an append buffer and then using its trickery to update that args buffer, modifying that args buffer can be really slow because we have to do it as an atomic operation. So if we're doing it 16 times, that's a lot more expensive than if we only do it once. Fortunately, we can only do it once per group because we know our index within the group and we have some group shared variables. So as an example, for each thread group, first we figure out what thread should draw, save it in a variable. Yeah, that's actually way more readable up there. That's good. So save in a variable if we should draw. Have our first thread in the group can sort of be thought of as the leader in many ways. Have it reset all the group shared variables. Each drawing thread will add one to a visible count. So this is a group shared variable in this case, and by performing an atomic add on it, we can increment it by 1 and save its previous value to some local spot that we can get to. The first thread is then going to add this new count, the new version of visible count, to the args buffer. So the number of objects we're going to draw has been increased by that amount, and we only had to do it once per thread. It's going to store the old value of that in its own local variable. And then each thread can get that, in a group shared variable. Each thread can get that group shared variable, add it to its index, and we've got a unique sort of index within our output batch, which we're drawing to. And so we can write it to there. If you want to see this in way more detail, you can check out a really nice talk last year on decimal visibility in Horizon Zero Dawn. I think that was also in the morning, and that was very difficult to follow at the time, but it's a good one to rewatch a couple of times and get the hang of. Though I will note, a lot of the trickery they do is relying on having shader model 6, or potentially being on a platform where you can directly call the GPU's hardware versions of the methods, so we weren't able to get a lot of those tricks. And this is a code version of sort of what we went through on the previous slide, so hopefully I might encourage, if you want to really get the hang of this, I'll post the slides on my Twitter. Feel free to go through and have a look and flick between. You can see where we're getting, grabbing our matrix, seeing if we should draw it, and local index there is our index within the thread group, so we can, that is the leader thread doing those things. We've got a few group memory barrier with group sync things here, so that's about making sure that the entire thread group is at the same point. I'm honestly not entirely sure if those were needed, but I put them in while debugging at one point because I couldn't get things working, and I haven't taken them out since. So if anyone knows, I'd be interested to hear. And yeah, pretty much, yeah, as I was saying, we're doing a few interlocked adds, which is our atomic add. So the first one there, interlocked add visible count 1 my count. That's get the visible count, add 1 to it, and then save what visible count was previously into my count. And yeah, otherwise it's exactly the same as explained on the previous slide. All of these methods we're no longer really in Unity territory so much, so you can get some really nice documentation for these in just HLSL documentation on the Microsoft website, for instance. So there's some good resources out there. So there are some other tricks that we did after this. In hindsight, I don't know if these were needed, but they felt cool and they made things run a tiny bit faster, so I mean, that's always good for me. We realized we can also take an offset into the args buffer when we call draw mesh instance indirect. So we can use a single args buffer and share it between all of our draw calls, and then just say, hey, look, this many byte into the array when you want to do your thing. We can also use a single buffer for all of the positions. And yeah, again, we can pass an offset into the other method, except remember, you can't actually use the Unity provided one for that. You need to set it as a material offset, otherwise your code will only work on Mac. And yeah, by doing this, we can actually get all of our culling to be done in a single draw call. So we also pass in a few extra things. I've got an extra buffer of these culling info structs, which sort of say where in the batch do we start, because it will need to be adding that to the draw count to find where it's going from. And some bounds in there, which previously we passed in as material arguments. Now we need to pass them in per object. And then we pass in an extra buffer of these input batches, which is so integers pointing to which of these informations to use per object. And so this is the same length as the transform array. And so if we set them to neg1 when they're invalid, we can pad it to the nearest group size, which is, say, 16 on our target platform. And that way each thread group is only dealing with a single type of object and can still be quite efficient and only need to write to an arg buffer once. On the right, you can see sort of some examples of how some of those lines from the last slide would change if we're accessing these. So once we brought in GPU culling as well, you can see how our frame times dropped from 69 or 90 milliseconds all the way back down to 32 milliseconds. And we've just beat 30 FPS, and that is our target on the device. In some cases, it'll be worse, but there's still way more we can do to look at bringing down the GPU time. So our wait for present on the main thread is only waiting on the render thread for like 0 to 3 milliseconds. The render thread is only waiting on the GPU for 2 to 8 milliseconds. There's a little bit of overhead we can still get back from bringing down our GPU time, but not too much. We're sort of approaching a point where the CPU and GPU are doing equal-ish amounts of work. And you can also see we're running our physics update twice because for some reason we're still running physics at 60 FPS in the game from PC, I assume, even though on Switch, on a arbitrary console platform, we have no chance, I think, of hitting 60 FPS, but maybe we'll give it a crack and see what we can do. Unfortunately, I can't really show you the GPU side profiling data because they're all unique tools for every platform, and I don't really want to go running around NDAs and that kind of thing. But I can tell you performing the high Z is actually preparing the high Z mipmap is the most expensive part of this operation. It's about 2 to 3 milliseconds, and it does require rendering the depth pass so when we render the depth pass, we're using all the culling results from the previous frame. So technically, our depth map might be a tiny bit wrong, but given we're using it for culling and this frame's like image effects, I don't really mind too much. This also means that the worst case scenario is that something won't get drawn into the depth map, which means it'll try to draw stuff further away than that, which means our high Z is going to be completely correct. It'll be conservative and it won't cull things it shouldn't. And that's a really nice attribute. Often what people will do with high Z is they will use the previous frame's depth map and then reprocess that, which means you need to use last frame's camera, which means if your camera's turned or something, you need to make some kind of assumption as to what's happening at the edge of the screen. But yeah, because we use our depth pass for our image effects and that kind of stuff, I'm actually not too bothered that it's being based off that. And we haven't actually attempted to optimize the high Z shader we got yet. We're using something fairly off the shelf for that. And the cull itself is actually super cheap. We're less than a millisecond to cull, the thousands of objects in this game. So that was a really nice result to see. I will note Feather's results using Unity 2017.4. So our initial testing on 2018.2 is actually looking much better even without this system. So the way we saw everything on one render thread before, that is actually spread across the job system now in 2018.2. I'm not sure, it might have been earlier in 2018. So that's nice to see that improvement's there. We haven't had enough time to do some testing and update. I didn't get a chance to update this presentation with that in mind, really. So we'll see how our instance renderer compares there, because really you'd hope that Unity can do a pretty okay job at rendering a bunch of static stuff, but we'll see what we can do to take sort of our domain-specific knowledge into account. The Table of Tails results are in 2017.2, and we're expecting to ship using that version. We're too close to release now to really want to be doing any major version updates. So yeah, I guess the real thing I want to take away from this talk is to think about what your game does and what it does uniquely that Unity can't optimize for. Because Unity is a great engine, and I've been impressed in the optimization we've done. Often we'll go in to optimize something that we think we can do smarter than Unity and find out that Unity's actually doing a really good job of it already. So think about what you do in your game or application which is different from the typical game, something that Unity can't assume, and then, so in our case, we don't need culling or whatever, our objects don't move, all of these kinds of things, and think about how you can sort of extend Unity even further and make your own stuff happen. So how are we doing for time? 25. So I've got a slide for questions, but I'll go over one last thing. So we had some performance issues in Table of Tails, and we had one particular bug where on PlayStation specifically, we weren't seeing this on PC. Eventually, if you kept playing for a long time, the frame rate would sort of start to tank. And for some reason, when I was trying to attach the GPU profiler, it was having a lot of trouble grabbing a frame that was valid. I don't know if we were doing something to corrupt it or whatever. But we could attach Unity's CPU profiler, and we could see it had something to do with our instance renderer. So it was a really painful thing to debug because it's something we weren't seeing unless we played the game for an hour. Eventually I had some time, I hooked up a logging script to list all of the batches and the counts in each scene. So this is sort of what we saw. So the first scene, we've got a bunch of these objects, 250 of each. In the second scene, we've got some new objects, but the old batches are still there with 2 objects in them. And at some point, some of you might start twigging on to what's happening here. And then we load into another scene, and we've got all of our old batches with 2 objects in them. And so eventually I figured it out, and I sent my colleagues some messages here. And it turns out those extra 2 batches on PlayStation that we were drawing to get around as a filthy hack, we never actually made our batch code clean up the batches when they only dropped to 2 objects on PlayStation instead of to 0. So yeah, that was a bit of a whoops moment, and we only solved this bug last week after we added our sort of filthy hack probably a year ago. Yeah. So that was in the game for a while before we eventually sorted that one out. So yeah, do we have any questions? No, cool. Well, I'm happy to answer any questions or any sort of GPU profiling or whatever else. There's a lot I didn't go into in this talk. If anyone has things they want to discuss, their own projects, happy to field some questions here or outside, or hit me up on Twitter. Yeah, thanks.